Welcome to the Kentucky Watershed Academy. This is Module 4 dealing with data, and in this presentation we're going to be focusing on quality assurance and quality control. In this presentation we want to provide an overview of quality assurance and quality control, look at a quality assurance plan and the different elements that it contains, explain some different quality measurements, and some elements of data screening. We should begin by stating that the reason we're discussing quality assurance and quality control is that these are an EPA requirement for any data collected for a 319H watershed plan and any data used for the Kentucky Divisional Water Use Assessment. Quality assurance and quality control are related concepts. They're separate processes, but they're intertwined. Quality assurance, or QA, focuses on the prevention of data problems through good policies. Quality control, or QC, focuses on detection of data problems that occur during the monitoring process itself and minimizing their impact. Examples of these two related concepts help demonstrate these separate but related focus areas. Quality assurance, or QA, includes procedures, audits, data verification, good data sheets, and similar items. These forms, procedures, and policies help ensure good, consistent practices. Quality control, or QC, includes duplicate samples or quality check samples, root cause analysis, or rejecting data that doesn't meet a certain threshold. These detect whether the data meet these standards for the project. Quality assurance and quality control is assured through a series of documents that move from very general to very project specific. A quality system is a policy or regulation that sets overarching requirements for a study. For example, 40 CFR 46 covers quality assurance on all federal projects. 40 CFR 31 and 35 covers uniform administrative requirements for environmental grants. EPA QA R5 and G5 have to do what is required in developing quality assurance management plans. A quality management plan document includes the general practices that an organization uses to ensure quality. For example, the Kentucky Department for Environmental Protection has an overarching document. Other organizations may have one as well. The quality system and quality management plan documents will inform plans for a specific monitoring project. Each project will have specific management, data collection, and data assessment methods customized for that specific project. These documents are called Quality Assurance Project Plans, or QAPP. The Quality Assurance Project Plan, or QAPP, will reference a lot of other documents that indicate how to perform a specific procedure, that's a standard operating procedure, a testing method, or to operate a piece of equipment. These guidebooks ensure that the data collection and testing method are repeatable and standardized. Some examples would be your habitat assessment procedure or the EPA method for analyzing ammonia. Finally, there are standardized forms that are used to document the data. This includes data sheets, custody logs, maintenance and calibration logs, review checklists. These forms and documents are used to track all information associated with the collection and testing in a standardized manner. For watershed planning, two EPA guides form the quality system. These specify what is required for a quality assurance project plan. The Commonwealth of Kentucky also has a quality management plan document. All these inform a template developed by the Division of Water that covers what is required in a QAPP for water quality monitoring to support a watershed plan. A QAPP is necessary for all EPA or Kentucky Division of Water approved watershed planning documents. So what goes into a QAPP? You probably will not be developing one as a watershed coordinator, but you might be involved in selecting the technical group who will prepare one. Therefore, it is helpful to have a brief overview of the contents of this document. Essentially, the document covers three basic areas: detailed description of project management and a plan for successful completion, a detailed description of how the data will be collected and analyzed, and how the data will be assessed for fitness of use and process for decision making. We'll examine each of these areas a little bit more in depth. The planning and management section of the QAPP covers an overall description of the who, what, when, where, and why, and how of the study. It sketches out the study goals, the purpose of each step, the objectives of the data, and the criteria for acceptance and action. We will elaborate a little bit more on the data objectives and indicators section. The data quality objectives indicate how good the data needs to be in order to answer the questions you are trying to ask for your study. This is specified by data quality indicators. These will be addressed in the next slide. Action limits are a list of critical levels such as regulatory limits, maximums of a laboratory test, or other levels that trigger additional investigation. All this needs to be known and specified before beginning a study. There are 6 major indicators of data quality. The graphic indicates the difference between accuracy, that is trueness, and precision, that is the tightness of the grouping. These data quality indicators will frequently be summarized in a series of tables. The indicators include precision, accuracy and bias, representativeness, comparability, completeness, and sensitivity. When we talk about water quality monitoring projects in general, there needs to be some awareness that often insufficient data is collected to make statistically significant statements about the reductions that are necessary in order to meet designated use requirements. There are sample size equations that can be used to calculate the number of samples needed to make a given decision. These equations account for the following factors. 1. The statistical power and confidence, the minimum detectable change, the mean and standard deviation, the water quality target. All of these factors need to be considered, and therefore there is not a one-size-fits-all for all projects. The number of samples that you need cannot be standardized. It depends on the question you're asking. An example is given regarding determining trends for E. coli. So, for example, you would need 250 samples to detect a 100 MPN drop in E. coli over 10 years with a starting mean of 300. This gives you an idea of the magnitude of samples that may be necessary. So for watershed planning, the data collected is generally insufficient for statistically significant statements about reductions. However, they are generally sufficient to give some general targets to focus best management practices on. So make sure, as you're working through the data, make sure to keep a 400,000 foot perspective. The second section of the quality assurance plan covers data collection. That includes the design of the study, specific locations, or at least the method for choosing locations, procedures, lab tests, equipment used, forms, and other items. Study designs for watershed planning will typically be targeted monitoring, but they may pull data collected for other purposes as well. The National Water Quality Monitoring Council has developed fact sheets on each of these different study designs. These are available on the website and summarized here in this slide. Each monitoring design has specific strengths, weaknesses, and products that will result. When it comes to quality controls, there are some quality controls that will be in almost every quality assurance project plan. This includes controls for precision, accuracy, and sensitivity. To measure precision, duplicates or split samples are used. Duplicates can be taken in the field, in which 2 bottles are collected, or one sample can be run twice in the laboratory. The difference between a duplicate and a split is a duplicate is collected in 2 bottles. A split sample, double the volume is collected in 1 bottle. A lab duplicate measures just the laboratory error, while the field duplicate includes the variability in the field conditions. Here you expect the results to be the same, so comparing the 2 results gives a percent difference for those measurements. So a result is never just a result, but a result is a plus or minus of some percentage. Measurements in the field, such as pH, dissolved oxygen, and other parameters, can also be replicated to provide similar data. To measure accuracy, there are 2 types of controls. On the left is a laboratory control, or a laboratory spike. On the right is a matrix spike samples. In both cases, a known amount of a pollutant is injected into either a blank, that is, water that's free from the pollutant, or a duplicate of a sample that's been collected in the field. In both cases, the test is to see how the amount measured or recovered during the testing procedure compares with what was injected into the sample. The difference between the laboratory control and the matrix spike is the effect of the sample upon the measurement. So, for instance, you might get some interference, or the color may be darker, or something of that nature. The percent recovery is usually given an acceptance range. For example, you want to recover 90 to 110% or 80 to 120% of the amount that's injected, depending on whatever the method is. If these samples are not in the correct range, the laboratory should be retesting to get acceptable results. To measure how sensitive a measurement is, or whether there has been contamination in the process, blank samples may be analyzed. Blank samples indicate contamination that may occur in the laboratory or in the field, as well as the ability of the laboratory to distinguish noise from a quantifiable result. Uh-oh. When it comes to evaluating sensitivity, for most methods, you cannot measure a true zero as a result. You can only say it is less than your testing ability, or indetectable. There are different ways to express how sensitive a test is. A method detection limit, or an MDL, is a level at which the signal is distinguishable from noise. At this level, you can detect the presence of something, but you cannot quantify it. Between the MDL and the RL, or reporting limit, results should be flagged as estimates. A reporting limit, or a limit of quantitation, is a level at which you can state an actual number with a level of statistical uncertainty. It is important that the laboratory indicates both of these levels for each test. Note that the reporting limit is a broad term. Some labs use a LOQ, or a limit of quantitations. Others use a PQL, or practical quantitation limit, and that includes the analyst variability as well. Generally, a reporting limit is about 3 times the method detection limit, or it's the lowest point on the calibration curve. Please note that if a sample is diluted, the reporting limit will be higher. All equipment, field as well as laboratory, must have a log of calibration and maintenance. This allows for tracing any problems that occur over time and can identify suspect measurements. This is an example of a field instrument calibration log. Where possible, to standardize the information recorded, data sheets should be developed. The third major section of the Quality Assurance Project Plan, or QAPP, focuses on data assessment, shown here in the brown. It includes what sort of actions are taken along the way to oversee the data collection process, including audits and notifying folks of problems. It also includes reviewing the data to make sure it is valid for the purpose that's intended. Here you can see a summary of the data assessment process. You look at your data as well as the quality controls, inspections, and audits to decide what needs to be thrown out based on predetermined protocols. You will want to indicate the type of statistical analyses to be used, how outliers will be identified, and what models the data will be plugged into, as well as other information. This describes how you will process the data to arrive at the end goal and what deliverable formats that end goal will take. So this concludes what generally goes into a QAPP document. So having given an overview of the QAPP document contents, I want to give you a brief overview of some data considerations when developing a plan. These include seasonality, flow and timing, rainfall sources, as well as looking at data qualifiers, how to handle non-detections, and some unit considerations. So first, let's look at seasonality. The Division of Water has requirements of monthly sampling for 1 year at its minimum for a basic watershed plan development. This is because water bodies can act very differently throughout the year. Think about the types of pollutants that may be coming from land uses in your area. Is the rainfall different in certain times of the year? Do people fertilize at certain times? How about applying salt to roads? When are people playing in the streams? When do critical periods for different organisms occur? Certain periods may require more attention. Think about this during your study planning. You also want to consider the effect of rainfall in your sources. Division water requires at least 2 wet events and 2 dry events for successful monitoring. This recognizes that pollutant concentrations are very different in wet weather versus dry weather. What is dry weather? How long does it need to be dry before a rainstorm comes through in order for it to qualify as wet weather at an event? This is described as an antecedent dry period and should be defined in your quality assurance plan. Thinking about potential non-point sources as well as point sources and how they relate to weather conditions is important. For instance, during wet weather, you'll get lawn or pasture, crop runoff, sanitary overflows, bank erosions. Whereas in dry weather, you're going to have more baseline sources, like perhaps a wastewater treatment plant effluent, or groundwater geology sources, or perhaps septic systems. You also need to consider the effect that flow might have in your sample collection. Here's an example of a storm event monitoring in the Wolf Run watershed in Lexington, Kentucky. Each of the different colors represents a hydrograph for a different site in the watershed, and each of the stars represents when the sample was collected at that site. From the time the stream started rising to the peak of the storm, it took 2 hours at the most. But the flow that is measured at the site is largely a product of when the sampler arrived at the location. If I'm trying to compare pollutant loads between sites, then I will have to have a more standardized way to adjust the flow. Otherwise, my pollutant loads will just be based on whenever I arrived at the site, because flow and concentration determine load. So especially if you're comparing samples collected on different days at different sites, so non-synoptic sampling, understanding the flow is very important. Otherwise, you'll be comparing apples to oranges in terms of your load ratios. All laboratories will have some sort of code system for qualifying data that is outside of the quality control limits. You'll need to decide what to do about different types of results. For instance, some results need to be thrown out and recollected. For others, the lab may need to to reanalyze. These decisions need to be thought through before sampling begins so that a proper response can be made during the course of the data collection period in the event of a problem. Even if you are only doing simple data summaries, you need to think through how to handle samples that are below detection limits. There are statistical guides, such as from the USGS and the EPA, that help inform decisions about how to handle non-detections based on the percentage of the data that are below the detection limits. However, assuming everything is zero versus assuming it is equal to the reporting limit can really bias the results, particularly if the reporting limit is close to the water quality standard. You also want to pay close attention to units. Sometimes data errors occur because the wrong unit is recorded. For instance, a conductivity meter may switch from millisiemens per centimeter rather than microsiemens per centimeter. Another common error occurs with nutrients. Sometimes phosphorus is reported in terms of the element phosphorus, so the milligrams liter as P, while other times it is reported as phosphate, that is PO4. Phosphate weighs a little over 3 times as much as phosphorus. So be sure to record the proper units when using as P or as PO4 in the ending. Similar issues can occur with nitrate, ammonia, or other nutrients. If the full unit is not recorded, the data is unusable. We began with the analogy of garbage in, garbage out. So how can you determine if your data is garbage? I like to refer to this as the smell test. It's a very basic screening to see whether the data is garbage or not. The smell test has 3 elements to determine if your data stinks. 1, a visual scan. 2, a scientific scan. And 3, a review for odd phenomenon. The visual scan means looking over the data as it is received to look for obvious errors. Sometimes the data may be entered into the wrong column of a spreadsheet, producing the impossibility of a negative pH result or a greater than 14 result for pH. You know this is an error. Sometimes you might pick up on a unit error in conductivity if the other measurements are around 900 and then one side is 1.2. It is likely that the meter switched units. Sometimes a decimal may be left out, or the sampler forgot to fill in a field, or the handwriting is sloppy. If you follow up quickly after the sampling, you can often have the sampler or the lab analyst make the proper corrections. If you start to notice a lot of these errors, you will want to be extra thorough with the data. Another scan is the scientific scan. This scan relies on cross-parameter checks on the numbers. While allowing for some accuracy or precision errors within the testing methods themselves, certain principles should always hold true. For example, TKN testing includes ammonia as well as other forms of organic nitrogen. Therefore, if ammonia is greater than TKN, you should have a follow-up with the lab to verify the result. Similarly, total phosphorus should be greater than orthophosphorus. So you can use this as a general check. If you have an E. coli result of greater than 2,420 and the lab did not perform a dilution, then you know there is an error because that is the maximum of the testing method. Likely, a dilution wasn't reported. Also, you can typically use your total dissolved solids as a check on your conductivity. If you have a full dissolved ion profile, so that is all the different metals and ions, you can do an ion mass balance. Typically, the TDS is 0.5 or 0.7 times the conductivity. Here's an example of what an ion mass balance looks like. There are some online calculators. I've placed the link below. But if you have a breakdown of the cations and anions, you can convert them into milliequivalents by multiplying by the charge and dividing by the molecular weight. The sum of the anions should be equivalent to the sum of the cations. Also, either one, the anions or the cations, times 100 should be equivalent to the conductivity plus or minus 10%. This can be a very helpful check on your laboratory data to see whether your data stinks or not. Does it pass the smell test? Lastly, we have the odd phenomena check. For instance, you might have a low flow and low dissolved oxygen. Follow-up discussion may indicate that the sample was collected from a pool. There may be an instance, one I've experienced, is where a beaver had constructed a dam 50 foot upstream and the dissolved oxygen was low because of the dam. There was not a dissolved oxygen problem, that was just a natural result. You might also have conditions in which there's a really high sediment numbers during low flow conditions, but the stream is not turbid. This might indicate that someone disturbed the bottom when collecting a sample. Low dissolved oxygen measurements on continuous monitoring sensors can occur because, for example, a snail attaches to the sensor or the sensor gets covered up with sediment. Just needs cleaning. Both of those I've experienced in real life. Be suspicious of data and investigate. Develop a nose for the data. If it smells fishy, look into it more and exclude results if necessary. In summary, basic quality assurance and quality controls mean that you are planning ahead to address errors that may occur during your project from start to finish so that you have a plan to respond when problems happen. As the old saying goes, if you're failing to plan, you're planning to fail. And we hope this gives you some idea of what quality assurance and quality control are and how to develop a plan to address those. Thank you.